comment there, but it happened. So I wonder what they're thinking, because it shouldn't work. And sometimes not only should it not work, but I wonder, how could I make it work? So originally when I did this panel, it was called Science of Anime, because there's these great shows on the Discovery Channel called Science of Star Wars, Science of Star Trek, Science of Batman. And what they try to do is they try to explain how to make things work using science. I did the panel under that name, and then I thought about it some more. You know, I really don't like those shows, because to try to explain those things, they actually go so far beyond actual good science that they have to go right back into the realm of science fiction. I don't really want to get back into science fiction. I want to teach science. I want to get good science here. So what I want to do is I want to put these things to the test using science. That's not Science of blank, it's blank Mythbusters. So I changed the title, and that's why the title is Anime Mythbusters now. So let's go ahead and get started. But first, I have a warning. Warning! This panel contains algebra, graphs, scientific notation, technical language, calculus, and inequalities. Put your head down for a minute, I'll explain what it means when it's done. A lot of times I have to do this panel on Sunday mornings, and I have no idea why they'd love to schedule me like really early on Sunday mornings. But to try to wake everybody up on Sunday mornings, I have a little bit of audience participation designed into this panel. I'm going to every once in a while ask, will this work? And I want you to all shout simultaneously, hell no, who thought that up? Okay, just make sure we're all awake. So now that we know what we're getting ourselves into, let's go ahead and get started. First topic I want to cover, oh my gosh, I think every anime screws this up. Something very simple that I hope we'd all be familiar with, called gravity. So I'm going to show a clip.
I can't see. Sorry, his head is in my way.
It's the scene as the children were clowns about the planet.
You're in the way! You're in the ears! Move! Come on, move! The door!
You can't see.
Thank you!
Yeah, there we go. Yeah, they're falling the entire time.
Alright, obviously I did not need to make the clip that long, but shit, Sephiroth. The illustrative principle I want to talk about. They're falling. Basically, if you haven't seen the movie, yeah, right. Big building, Sephiroth cuts a big chunk off, and they are standing on the chunk, and it starts falling. Yet, if you were watching carefully on the itty bitty little thing that I don't know how to blow up for some reason, I'm actually using OpenOffice, not real PowerPoint. Woohoo! So they're walking around on this falling block like there's gravity. Well, yes, there is gravity. That's why they're falling. So the problem with this is that it doesn't work. Again, I showed this nice pretty clip, and it was distracting. There was Sephiroth, great music, Nobili Manto, and all that. So let's simplify it. So to simplify this and try to make it a little bit more digestible, I made my own little custom animation to explain this a lot better. It doesn't have any great music, so I'll go ahead and narrate. One day, Bowser kidnaps Luigi. To save the day, Bowser flies off in the sky. Fortunately, bars start falling from the sky. Mario hops up them and saves the day. Da, 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 da. So why doesn't this work? I hope you're all awake.
Because bars don't.
Everybody brushed up on their integral calculus, right? So if you guys took high school physics, this part might look familiar. If you have an object, there's two forces going to be acting on. You got the force of gravity being directed downwards, but there's also going to be some resistive force pushing back up. That is going to be dependent on the mass of the falling object, how fast it's falling, and some sort of other constant, which I call K, which is just some sort of constant that has to do with how viscous the fluid is. Obviously, it can fall a lot faster through air than you can through water. So K will be lower for air than it will be for water. We're not going to worry about what it really is for air. We just want to kind of get a feel for how things are going to work. So this is what I do. I start off, I just use Newton's second law. F equals ma, but we also got this other force in there, the kmv. I set things negative because we're directed downwards, and then I go through some math. Basically, I take this factor out of m, set this equal to the calculus version, integrate both sides, start tossing in natural logs because that's how you integrate that nasty stuff. Go, 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 go. Equations. Yay! All right, so that's what that equation means. Yay! It looks scary, but it's not. Here's why. G is a constant. K is a constant. K constant, K constant, K constant. E is a number. We also have C, which is the constant of integration. The only thing that's actually a variable here that we really care about is this T. So if we take this and start making T bigger and bigger, what happens to this equation? Well, since this is a negative exponent means it's going to go the opposite way of what we normally expect. So if we're making it bigger and bigger, this whole thing's going to go smaller and smaller. Which means as T gets really, really big, all of this goes away. And all we're left with is negative G over K, which means that the longer you fall, you're going to start approaching some constant. So let's graph it. Graph. Not falling very fast at all. And then we fall faster and faster and faster, but then we start leveling off. I'm guessing you've probably heard of this. This is known as terminal velocity. We don't talk about this in airports. But what this means is that if something started falling, and then something else started falling later, one thing you can notice about this equation, we lost the m's. The m's are gone. It doesn't matter what your mass is, it just depends on how long you've been falling. So if something else started falling later, regardless of its mass, it will never catch up because its curve will match this. Which means that if they aren't catching up, if they don't have some accelerating force between them, there will be no force to push them together. If there is no force to push them together, there is no force of friction. Which means you can't walk on those blocks, let alone, if you started falling later, ever even catch up to them. So let's go back to my animation and see how this would really work. One day, Bowser kidnaps Luigi. Mario rushes onto the scene to save the day. Bowser flies off in the sky. Fortunately, bars start falling from the sky. Reality to get that's my first topic.
Overruled by science.
Busted by science. Next up, how many of you have seen Gurren Lagann? Not enough. Alright. This is going to be a clip from the last episode. Don't worry, it's not spoilerific. But one of the things, if you ever do watch a series, you will learn very quickly is their mechs keep getting bigger and bigger. It's a very good manly paradox. By the time you get to the last episode, it gets really big. This is a planet. This is a solar system. This is a whole bunch of solar systems. It's, oh my god, it's a galaxy! That's a bunch of galaxies. That's a bunch of galaxies, but there's one main one. That is a big freaking mech.
Yeah!
Mr. Owl, how many galaxies would it take to make something that big? I looked at that and go, man, that's got to take a lot of manufacturing. Where are we getting the raw chemicals to be able to do that? China?
Taiwan! Where are we getting the fuel?
Even if we took our whole planet, and tried to make something that big, we would be long. We couldn't even make his toenail with our planet. We're going to need to cannibalize a whole bunch of galaxies to do it. Let's figure out how many.
Yeah!
So what I want to do for this is scale up something I know about. Cars are easy to find out about. There's lots of stuff on them on the internet. I can't find anything about how to make a galaxy-sized mech on the internet. So let's start with something I knew. A car. A car has, a good amount of steel in it and stuff. So let's scale it up first. First, I estimated how big a car is. About 5 meters long. How big's a galaxy? Well, about 5.3 times 10 to the 46 light years. What the heck does that mean? First off, we got this weird thing called light years. What's a light year? Light year is the distance it takes light to travel in 1 year. Light travels 300,000 meters every second. Think about how far it's going to go in a year. That's how far a light year is. And then we have this 5.3 times 10 to the 46 coming up after. What the heck is that about? That's scientific notation. What that means is you take a 5.3 and add 40. Grab the zero. Sorry, I'm looking at the small screen and it's blurry. 16 light years. So that means you're going to have 5.3 followed by 16 zeros that's how many cards you'd have to stack end to end.